Hey guys, today we will solve problem 2 from the European Girls Math Olympiad 2021. We are asked to find all functions f from the rational numbers to rational numbers such that for all pairs x and y in the rational numbers we have f of x plus y is equal to f of y plus x squared. If we take a look at the given equation, we see that it basically tells us that changing the argument or increasing it by x times f of x increases the output by x squared. We can reapply the same argument to obtain that for any sequence of xi, we have that translating our argument y by the sum of I going from 1 to n of xi f of xi changes our output by a sum of xi squared. We notice that if our sequence of xi is non-zero, then this sum is greater than 0, and therefore these arguments can never be equal. In other words, this sum, the sum of xi f of xi, is not equal to 0. This gives the intuition that for all such values of x f of x must either always be positive or always negative, and we will come back to that later. Moreover, looking at this equation, we see that if we plug in y minus x f of x for y, then the left side will become f of y. So let's take a look at what we will obtain. P of x comma y minus x f of x gives us, as I said, f of y is equal to f of y minus x f of x plus x squared. We see that by rearranging this equation, we basically obtain, or exactly obtain, that f of y minus x f of x is equal to f of y minus x squared. This is especially nice if we combine it with our first idea of using induction. Namely, if we set all xi equal to x here, then we get that f of y plus t times x times f of x equals f of y plus t times x squared for every natural number t. And now we can use the second equation to also do induction in the other direction to obtain that this equation holds for all integers t. We conclude that q of x, y, t holds for all integers t, where q of x, y, t is f of y plus t times x f of x equals f of y plus t times x squared. One more thing I want to notice is that we want to try plugging in minus x for x. Firstly, that's good because it doesn't change the right side of our equation. And secondly, it will give us something similar to this here. In particular, p of minus x comma y is f of minus x f of minus x plus y equals f of y plus x squared. In conclusion, translating the argument by minus x f of minus x increases the output by x squared. If we then translate by minus x f of x, we decrease the output by another x squared and therefore land where we began. And therefore it is a reasonable assumption that the argument doesn't change under that operation. And that is why claim 1 is that we will try to prove that this translation of argument is equal to 0. In other words, for all x not equal to 0, we have f of minus x equals minus f of x. As I said, the key equation for this will be that f of y minus x f of minus x f of x is again equal to f of y plus x squared minus x squared, which equals f of y. Let's assume that our claim is false. In other words, that we can find an x not equal to 0, such that f of minus x plus f of x is also not equal to 0. And then this value, which I'm going to denote by d, is not equal to 0 as well. In this case, we can do induction in both directions to obtain that f of y equals f of y plus t times d for all t in z. But we know, for example, that adding a t times f of 1 to our argument changes the output if t is not equal to 0. We can bring these two equations to a contradiction because we are working over the rational numbers. For that, consider integers a and b such that a divided by b equals f of 1 divided by d, and then we have b not equal to 0. So we have ad equals b f of 1, and hence we can use our equations to obtain that f of y equals f of y plus ad by that equation. That is now equal to f of y plus bf of 1, which is equal to f of y plus b. And this is a contradiction to b not equal to 0, and therefore the claim is proven. Notice that we get f of minus x is equal to negative f of x only for x not equal to 0. But we can complete this in the following way. We have this and that equation where we have like kind of opposite signs if we set y equal to 0, and this will help us out. So let's set y equal to 0 and x is equal to 1 in both equations, which on the one hand yields f of 1 is equal to f of 0 plus 1. And moreover, we know that f of 0 is equal to f of minus f of 1 plus 1. We can see that this argument can't be 0. Otherwise, we would have f of 0 equals f of 0 plus 1, which can't be true. Therefore, we can use claim 1 to obtain that this equals negative f of 1 plus 1. But we know that f of 1 equals f of 0 plus 1. So all of this is equal to negative f of 0. In conclusion, we know that f of 0 equals negative f of 0, and therefore f of 0 is equal to 0. This is quite strong. Namely, we can set y equal to 0 here to obtain that f of t times x f of x equals just t times x squared. What we would like to do now is to set t equal to 1 divided by x, such that we get an f of x on the left side. This is, however, not always possible, since t must be an integer. And the solution will be to write x equal to p over q, and then set t at least equal to q. With y equal to 0 in equation q, we obtain that f of q times p over q f of p over q is nothing but q times p over q squared. In other words, f of p times f of p over q is always equal to p squared over q. Now that we know the value of f of p times f of p over q, we can set x equal to p times f of p over q and y again equal to 0 in our original equation to obtain that f of p over q times p squared over q is equal to p f of p over q all squared. Notice that this argument is just p squared times p over q f of p over q, and so this left side is the same as the left side of q of p over q 0 p squared, which tells us that f of p squared p over q f of p over q, which is exactly that, is equal to p squared times p over q squared. In conclusion, f of p over q squared equals p over q squared, and thus f of x always equals plus or minus x. The last step is to show that f of x either always equals plus x or always minus x. Both of these are indeed solutions to our functional equation. And here I want to remind you of the initial intuition that we got, that x f of x is either always positive or always negative, which we use to finish the proof. So let us assume that we find non-zero x and y with f of x equal to x and f of y equal to negative y. We will use this idea together with the fact that we're working on the rationals to bring this to a contradiction. We start with setting y squared over x squared equal to a over b, where a and b are non-zero integers. Equation q with t equal to a gives f of a times x f of x is equal to ax squared. This is by squared, and so all of this equals f of by f of y. We know that by f of y equals minus by squared equals minus ax squared equals minus ax f of x, and therefore all of this is equal to f of minus ax f of x. This is equal to negative f of ax f of x, and therefore we can conclude that f of ax f of x is equal to 0, but we know that f of x is plus minus x, and so a times x f of x equals 0. This is clearly a contradiction, since a is not equal to 0, and f of x equals x, and this is also not equal to 0, and so our assumption was false. In total, we know that the solutions are f of x is always equal to x, or f of x is equal to negative x, and therefore we are done.